What if I were to tell you that I have special powers, that I can flip your quarter without cheating, and with the powers of my mind, make it come up heads every time? Say you gave me a quarter and I flip it. You see me do it, honestly, and it comes up heads. Do you accept this? Think about this. How many times would I have to do it in a row for you to accept it? I can guarantee that in a class this size, we would have hundreds of different answers, probably ranging all the way from 1 to eternity. Obviously now, one time could just be by chance. And if we did not accept it, regardless of how often we test it and see it, we would never advance in science at all. So what number is the wise one to accept? We have a way to test for this, and this is called significance testing. In research, this question often comes up when we end up with two means. So with the cockroach audience effect study, it took the cockroaches an average of 5.38 minutes to complete the maze with an audience, and an average of 6.75 minutes without one. 5.38 versus 6.75 minutes. Now, the two numbers are different, but different enough to claim an effect, or just different a little due to chance? To answer this, we do significance testing. We compute a p-value, p-value, which takes into consideration the two means, the size of the two groups, and the range of scores in each group. This p-value is a number that gives the percent probability that the difference between the two means is just because of chance, not a significant effect. So are you hoping your p-value will be large or small? Think about it. Unlike a correlation coefficient, we want it to be small. You might think pea-sized. You're hoping your p-value will be pea-sized. And here on this slide is the consensus of the scientific community. If the p-value is less than 0.05, this means there is less than 5% chance that the difference between the two group means is simply due to chance. In reverse, this means there is a 95% chance that it is due to the IV, sleep deprivation, in our example study, for instance. So less than 0.05 is interpreted as a significant effect. Hooray! We are hoping our p-value will be pea-sized. Now, if the p-value is greater than 0.10, meaning 10%, this is interpreted as not significant. Okay, that's nice and clear, but what if it lands somewhere in the middle? If the p-value is somewhere between 5 and 10%, in other words, 0.05 and 0.10, it is interpreted to be marginally significant. But don't let this fool you. Marginally significant does not mean that it is almost significant. Instead, it means two things. One, you must withhold judgment, and two, collect more data. Understand, the more data you get to compute your p-value, the closer it moves towards the truth, whether that be lower or closer to significant, or higher, closer to not significant. Don't get this confused with interpreting a correlation coefficient taught earlier in this lecture. This is how to interpret a p-value. Very different. By the way, I would have to to successfully flip heads about 100 times consecutively to evidence mind control, which no one has ever done. Now is your chance to prove to yourself that you can accurately interpret a p-value. This TYL is pretty quick and easy, so you get 1 minute for this challenge. Go. Okay, let's quickly go over these answers. Number 1 is not significant. Number 2 is significant. Number 3 is marginally significant. You remember what that means? If not, be sure to review it, because it does not mean almost significant. Number 4 is significant. Number 5 is wow, really significant. And number 6 is not significant. Now, here's an interesting question. Why do you think it is that there is no such thing as a p-value of 0? The answer is because we don't know anything for absolute certain. We might test the theory that the sun comes up each day and get a p-value of 0.001 because it always does over the days of our study. We can pretty much count on the sun coming up tomorrow. But the truth is, we never know for absolute certain, right? And that is why there's no such thing as a p-value of 0. Here's another really interesting question. Why have more than one dependent variable in a single study? Now, a good answer would be why not? Because it's super efficient. Think this. If you could think of 2 possible things that sleep deprivation could cause, and you tested both of them in the same study with the same participants and the same researchers collecting data working, you've saved a lot of resources, right? And here's one more. Why have more than one independent variable in a single study? Now, let me give you a clue. This time, the best answer is not efficiency like it was before with the dependent variable. Although it would be more efficient, there is a more important, better answer here. To look for possible interactions. Why is there a warning on Viagra ads for men not to take it if they take nitrates, even though the effects on the sex lives of elderly men are positive if you tested both of them by themselves? The interaction taking both at one time can be fatal. By the way, do not miss the study sheet posted with your last online part assignment in your to-do list this past week. You read about many things that can go wrong in studies and many ways to protect for them. Be sure you did not miss printing the sheet posted in this last week's to-do list. You will want to study it, guaranteed, before your next proctored exam. This concludes the lecture portion of our class session today. Next week, we will look at old white guys in psychology. In other words, history of psychology.